Let's run through complete solutions to free response problem number 3. That's the first non-calculator problem from the released 2012 AP Calculus AB exam. This problem is all about your fundamental theorem of calculus and demonstrating that you understand what a function's first and second derivative tells you about the behavior of that function. Parts C and D are kind of tricky. Let me know how you get on with those. But apart from that, let's dive in. Throughout this problem, we're given a graph f that is made up of straight line segments and a semicircle, and we're using that to cook up a function g. Now you'll see that g is defined to be a definite integral from 1 up to my variable x over the graph of f. That should be making me think fundamental theorem of calculus. That's my area so far function. I'm thinking that's probably gonna crop up. In part A, we're asked to evaluate this function g at two values, namely x equals 2 and negative 2. Let's see how we're going to tackle that. So as I pointed out, we have this variable x appearing as the upper limit of our integral. So when I want to figure out what g of 2 is, I'm going to plug in 2 into that upper limit. And now all it's asking me is, what is this definite integral of my function f? Well, I'm starting at x equals 1, and I'm moving up to x equals 2, and I'm being asked to calculate this definite integral, which we should always remember is the area under the curve of the graph, in this case f. And it's really nice because for this portion of the graph, what I get is this nice little triangle sandwiched under the x-axis. I remember the area, the formula for the area of a triangle. I can just pull that out here, get going. So the formula for the area of that triangle is going to be half the base, which is length 1, times the height, which in this case, you can read off from the graph, is 1/2. I'm almost done, but I do need to remember that triangle is sitting below the x-axis, so when I calculate its area as a definite integral, I need to have a negative sign. It's a negative area because it's underneath the x-axis. So in this case, my answer is just negative 1/4. Now, I'm always going to fully simplify my answers as we're working through them today, but remember the AP often does not care if you fully simplify your answer or not, so don't waste time on that under exam conditions. For g of negative 2, it's going to be a similar calculation with a little twist. Okay, so again, I'm substituting that x variable for negative 2. Again, this is going to be an area under my curve of f, where the endpoints are x equals negative 2, running up to x equals 1. So in this case, the area under the curve is, I have this triangle and then this semicircle. Again, those are nice, well-behaved areas that I know formulas for the area of. But this is the tricky part. They're going to want you to make a mistake on, so don't. The way that we think of a definite integral as representing an area always assumes that these limits, upper and lower, have the smaller limit down below and the larger limit up above. So you can see here that negative 2 should be at the bottom. So we're evaluating this definite integral somehow in reverse. We're looking at the area the wrong way round. So what we need to do is write this integral the correct way round with its limits smaller to higher. But the price I pay for doing that is I have to choose a negative sign. I really was working backwards, working in reverse. So as long as I remember that negative sign, I will be in good shape. So I've got that negative. I'm now going to work out the area of the two shapes that I see. So I first of all have my triangle. That's going to contribute a positive area because it's above the x-axis. So it's a half times the base of 1 times the height of 3. And now I need to account for the semicircular area that is below the x-axis. Below the x-axis will contribute a negative area, so I'll subtract off That circle has radius 1. If it was the full circle, it would be pi r squared. So pi times 1 squared. But it's only a semicircle, so I need to only worry about half of that area. Again, if I simplify this all, I will get pi by 2 subtract 3 over 2 as my final answer. So how are the points going here? Well, it's straightforward. You're going to get 1 point for your first correct answer and 1 point for your second correct answer. On to part B. Looks quite similar. We're being asked to evaluate the function g or its derivatives at some specific x inputs. But this is where the fundamental theorem of calculus starts to rear its head. So I mentioned initially that this function g is making me think of the fundamental theorem of calculus anyway, because it's being defined as an integral of the function f. So to get from f to g, what I'm doing is integrating. The fundamental theorem of calculus just says to undo that process and get back to f. What I'll do is differentiate. So first things first, the fundamental theorem of calculus tells me that the derivative of g is just going to give me that function f straight back. So in particular, if I want to know what g prime of negative 3 is, that is just f of negative 3. And I can read that straight off the graph. So at x equals negative 3, I'll read up at this point on that nice straight line segment, and I'll see that my answer is 2. Done. What about g double prime, the second derivative evaluated at 3? Well, g double prime of x, that's what I get if I take the derivative of the left-hand side up here. So that will equal what I get if I take the derivative of the right-hand side. So that gives me f prime of x. And we just need to remember this is the slope of the function f. So in particular, if I want to know g double prime of negative 3, that will be f prime of negative 3. So I want to know what the slope of f is at x equals negative 3. Well, we're in luck because at that point on the graph, x equals 3. I've got a nice straight line segment. The slope is 1. I can work that out from the graph. So in particular, that is my value. How are the points divvied up? Well, again, we are getting 1 point per answer. Part C asks quite a lot of us. We're asked to find all the x values where g has a horizontal tangent. Not only that, but for each of those x values, I'm supposed to find whether there's a relative maximum, relative minimum, or neither at each of these x values. So, if we take that one step at a time, it's not too bad, I promise. First things first, for a horizontal tangent, we need to know that that means the derivative of g is supposed to be 0. Well, remember, from the previous part B, the fundamental theorem of calculus tells me that g prime is just f. So in particular, if I want to know where g prime is going to be 0, I just need to look at the graph of f and see where f is going to be 0. That happens at 2 separate places. It happens right here at x equals negative 1 and at x equals positive 1. So there are horizontal tangents at x equals negative 1 and x equals 1. Okay, first half is done. Now I need to find what kind of behavior g is showing at these x values. Do I have a relative min, relative max, or neither? Well, for that sort of thing, I know I need to be looking at the sign of g. So let's take each point, sorry, the sign of g prime, rather. So let's take each point in turn. So at x equals negative 1, notice that g prime of x, which is f of x, as we already decided, changes from being positive values, right? F is above the x-axis, changes to negative values. F, therefore g prime, changes to negative values. So since g prime changes from, in this case, positive to negative, what does that look like? Well, I know that at this point on the graph, I'm supposed to have a horizontal tangent. The behavior changes from increasing, g prime being positive, to g prime being negative, so g is decreasing. So that means that I have a relative maximum. That's what's happening at x equals -1. What about at x equals +1? Well, there, g prime, f, starts off negative, but then it remains negative on the other side of x equals 1. So that means that at x equals +1, because g prime does not change sides, neither a relative max nor a relative min occurs there. And that's us done. Let's see how the points were divvied up here. So we got 1 point for even just knowing that we were supposed to work with g prime being 0. That's 1 point. We got our second point for finding these x values, plus or minus 1. And for our final point, we needed to have our answer, not only the relative max and neither, but we also needed to have this explanation, this justification about changing sign or not changing sign. So you really had to work pretty hard to earn that third and final point. Okay, home stretch, final part, part D. Here, we're asked to find the x values at which g has an inflection point and explain our working. So, for inflection points, I know that means I need the second derivative either needs to be 0 or does not exist. Well, in a previous part of the problem, we already worked out that g double prime of x is the first derivative of f. And that's what we're going to work with again here in part D, because again, this is the slope of the function f. So I want to know where the slope of f, looking at the graph, is either 0 or does not exist. Well, scanning along the graph, I see I have a horizontal tangent at x equals 0. No other horizontal tangents, but there are a couple of places where f prime doesn't exist because I have a sharp turn in the graph. I've got a corner occurring at x equals -2, and I've got another sharp corner occurring at x equals 1. So that tells me my possible inflection points are occurring at x equals -2, 0, and 1. Well, are they all inflection points? How am I going to explain and justify? That's what's left for me to do. Well, notice that on either side of these three x values, g double prime, f prime, is changing sign. Okay. So here, on the left of x equals 2, the slope of f is positive. And on the right-hand side of x equals 2, the slope is negative, the slope of f. So that means that g double prime is changing sign. Similarly, if I look at x equals 0 on the left, f prime is negative because f is sloping down. On the right-hand side, f is sloping up, so f prime is positive. Again, my g double prime is changing sign. And similarly, over here at x equals 1, f prime is positive because f is increasing. On the other side of x equals 1, f is decreasing, so f prime is negative. So these are all since g double prime, which remember is really just f prime, changes sign at each x value. So for here, there were 2 points up for grabs, one for the correct values and one for the justification of g prime changing sign. And that's us done. So what did you think? How did you get on? Did this marathon of Fundamental Theorem of Calculus trip you up? Let me know in the comments. Keep an eye out for more free response problems from this exam and other exams coming up soon. And if you want to see my run through of the multiple choice problems from the 2012 exam, I'll put a link here. Very much looking forward to seeing you next time.